Hi everyone, welcome to our channel. Today we are going to solve the minimum number of swaps to make the string balance problem, and also we will be comparing the code for longest valid parenthesis problem with the present problem. So let's see this problem. The problem says that you are given a zero index string of even length n, and the string consists of exactly n by 2 opening brackets and n by 2 closing brackets. So this means that the string only has opening and closing brackets, and that too only one type of bracket, that is square bracket, and we just have to rearrange it without any addition or deletion. We have to make it balanced. Now, what is the condition for balanced? So first, it's an empty string, then it's valid. And if there is a concatenation of A and B, where A is also a balanced string and B is also balanced, so that can also be a balanced at last. And let's say if there is opening and closing bracket inside that, if we put a balanced string, so that's also a balance. So basically, we have to swap the brackets and rearrange them such that it becomes balanced. But in all those swaps, we have to find minimum swaps to make it balanced. So in the next step, let us see some more examples to understand this question better. These are some of the examples of the given problem. Now if we see in example 1, we need only one swap, that is the red brackets, and the string will be balanced. So that's why the output is 1. Now in the second example, we can swap the red ones. So after one swap, this is the string, and we can see that the yellow will also get automatically balanced, this one. So that's why only the brown one remains. So if we swap again, so that's two swap operations. First is the red one and then next is the brown, and the whole string will get balanced. Now in this we can also swap all these three. So that becomes three swaps, but we need minimum swaps to make it balanced. So that's why the answer will be 2. In the example 3, we can see that there is also again one swap needed. So then the string will become valid. That's the red one we have to swap. So that's why the output is 1. Now seeing these examples, can we get some inference? So one is that we have to think about any invalid case. So whenever there is invalid, like the closing can be more than opening, if we are going from left to right. So at that time, we have to increment the swap, or we have to swap at that time. So that is one of the inference that we can get. Now, whenever we have to think about invalid case, definitely we have to track opening and closing brackets, because let's say we are going from left to right, and from left side, definitely the opening brackets can be more, but the closing cannot. So we can use that condition to track the invalid cases. So let us think about more inferences using this example in the next step and note this down. So following all are the inferences for using the examples for the given problem. Now first is that we have to keep track of opening and closing brackets, and why we need that, so that we can find a invalid case. And let us say we are iterating on a string from left to right. So the opening brackets can be more, but the closing cannot. So if the closing is more than opening, then definitely that is a invalid case. So that invalid case can be an indication that we have to swap it. So one point that we can keep in mind to design our algorithm is that we have to count the invalid, and that will automatically become our minimum swaps. Now, so this is the one inference, and in the next step, let us design our algorithm using this inferences. So this is the algorithm that we'll be following, and in this algorithm we will be going from left to right. That's we are iterating, and if it's opening bracket, then there is opening B, which is the counter, and we will be incrementing it. And if there is a closing bracket, we'll be incrementing closing bracket count. Now, for handling the invalid case, this is the condition. And if closing bracket is more than opening, as we are going from left to right, so we will be incrementing the swaps. So because it's an invalid and we have to swap to make it a valid string. And then we'll be also incrementing opening brackets, but decrementing closing bracket. Now, why is that? Because let us see this example. So in this example, we can see that, so this red one is our pointer, let's say some I, and this is the bracket that we have already iterated. So here to balance it, what we have to do, we have to swap with one of the closing brackets, and it is an invalid case. So if we iterate this, what will happen? The closing bracket count will increase while the opening will still remain 0. So that's why it will come inside the invalid condition, and the swaps will be incremented. Now, opening, why it will be incremented? Let's say we have swapped it. We are just visualizing it. So we can see that the opening came in the past of the pointer. So that's why we are incrementing opening bracket. Now, a closing bracket decreased in the past. Why? Because we have swapped it. There was a closing bracket in past, but we actually swapped it with opening. So closing got decremented. So that's why we are decrementing closing. Now, whenever we come out of the loop, we will be returning the swaps count. So that will be our answer. Now, let us try on with this example and see how the algorithm goes. So first we have a closing bracket. So we have a closing bracket. So let us increment the count of closing bracket. And we can see that the third condition will also execute. Why? Because the opening is 0 initially and the closing is 1. So in that case, we'll be incrementing our swaps count, and then we'll be decrementing our closing brackets, and we'll be incrementing this opening brackets. Let us make it as 1. Now, this is our first iteration. Now, again, it is a closing bracket, so let us increment it. Now, we can see that opening and closing are kind of same, so we won't be changing it. The swaps won't be changing. And again, we have a closing bracket. So as we have a closing bracket, let us increment it. So we can see here. So we can see here the closing is 2 and opening is still 1. So definitely it will go into the third condition and increment the swaps. That is 2. Basically, swaps will be our answer at the last. And we have to increment opening brackets, that is 2. And we have to decrement closing brackets. So that will be 1. Now we'll go to the next iteration. So we can see that we have opening bracket. So let us increment opening. So we can see that 3 and 1. Opening is still more. So there won't be any modification in the swaps. Again, opening bracket. So it will be 4. There's again opening bracket. So it will be 5. We can see that the opening is more than closing in all the steps. That's why the swaps won't be changing. And at last, we'll be coming out of that for loop and we'll be returning the swaps. So the last answer is 2. And we can see here. So yes, it's 2. Why it is that? Because, so let's say we swap the first bracket and the last one. This and this. So how the string will be resulting is, so string will be something like this, correct? So we can see that these two brackets are not balanced. So in one swap, the full string except these two are not valid. So in the second, we will be swapping this. So that's how we'll be balancing this string. And in the next step, let us understand this condition in more detail, that why we have to increment opening brackets and decrement the closing brackets. Let us take the same example that we used for dry run. So why do we need these two conditions that are highlighted? So let us say we have, okay, in the screenshot you can see it's first iteration when I was equal to 0. So we have iterated the first closing bracket, and before this condition was executed in loop, there were two statements. That is, if it's open bracket, increment the open, and if it's a closing, uh, increment the closing. So closing is incremented and opening is still 0. So that was before this if condition. Now after that, after executing this, it becomes opening as 1 and closing as 0. Why is that? So let us take this first swap case. So in this, it's already swapped, so it is after swapping first. So it's just visualization, it's not the algorithm that it is doing. Algorithm is just keeping the count. So this is the my pointer. It has already iterated this bracket. So after swapping, we can see that these two are swapped, the red one. So in the past, we can see that there is an open bracket that we got. So that's why we incremented opening bracket. Now there was a closing here, but the closing went into the future, which we will be iterating in the future, and that's why the closing got reduced, which we have already taken in the closing bracket. So that's why we decremented it. So when we see this case, now the opening and closing are correct after swapping with this count, opening equal to 1 and closing equal to 0. So that's why after we swap, the opening gets increased while the closing get decreased because the invalid case is more closing and less opening. So that's why we do this two operations. And in the next step, let us see the Java code for this. In this Java code, we can see that there are three variables we have, and we are iterating the full string uh, from I equal to 0, that's from left to right. And then whenever there is a opening square bracket, we'll be incrementing opening B, and closing B will be incrementing because there is only the closing bracket that is left other than the opening. And whenever this invalid condition occurs, we'll be incrementing the swaps, incrementing the opening bracket, but decrementing the closing. So as we explained in the previous, why we are doing this too. Now, after the loop is completed, now our swaps will be having the count of how many minimum swaps we have to do. Now we'll be returning the swaps. So that will be our Java code. In the next step, we will be seeing the complexity analysis of this question. So here is the complexity analysis. Now, if we see the time complexity, so we can see that there is one for loop and it's going till n, that is the length of the string. So that's why the time complexity is O of n. Now space complexity is O of 1 because we have only three variables. So that's why the space complexity is O of big O of 1 and time is big O of n. Now in the next step, we will be comparing it with longest valid parenthesis problem and see what are the similarities and how we can manipulate longest valid parenthesis code to get this Java code, because the main concept is same in both. So let's go to the next step. So if we compare it with longest valid parenthesis, that is A, and B is minimum number of swaps to make the string balanced, we can see that we are iterating a full string from left to right in both of them. So that's one similarity. And then whenever there is an opening bracket, we are incrementing one of the counter, and again incrementing the other counter if there is a closing bracket. Same we are doing here. So these are the three similarities. And then going to the fourth, so this is an invalid case that we are capturing. And in the B also it's similar because we are doing some different logic inside that if condition, but the basic structure remains the same in both of them. So this was a comparison between these two, a same concept behind that. So if you liked our explanation, do hit like and subscribe our channel, and till the next video, thank you.